Hello, so in today's video, we're going to look at small angle approximations for sine, cos, and tan. So these are approximations we can make for the sin, cos, and tan functions when theta is a small angle in quotation marks. So in the questions, they will say, assume that theta is a small angle, give an approximation for some kind of function. So yeah, this term small angle is very vague, but in the exam, they will say, when theta is a small angle, approximate some function, some value. So the approximations that you need to learn are that when theta is a quote small angle, sine theta is about theta, cos theta is about 1 minus theta squared over 2, and tan theta is about theta. I mean, if you think about like a sine graph, for example, sine goes like this. So when your theta is a small angle on the x-axis at the start here, it's approximately the same as this y equals x line or this y equals theta line, if we call this the theta axis. So that's kind of a justification you can use for that one. And likewise with the tangent graph as well, tan goes like that roughly. So again, roughly approximately at here, this is kind of like the y equals x line or the y equals theta line, if that's called the theta axis there. And then the cos one is kind of like a quadratic, so 1 minus x squared over 2 or 1 minus theta squared over 2, depending on what you call the x-axis. So it's kind of like a quadratic. And when theta is small, like these small angles here, it kind of does look like a quadratic graph with a y-intercept of 1. So that's kind of like a justification, a rough justification for why these approximations are true. And you need to learn these 3 approximations. However, we can actually try and justify them properly. So let's draw a sector like this with an angle theta in radians, and it's a small angle. So we've got this arc length over here, this like arc length there. And this arc length, because the angle is so small, we're going to assume that's so small, it's approximately equal to the height there. So the arc length is approximately equal to the height. That's one thing we're going to note, about the same as the height. Now, arc length, to calculate arc length with a sector in an arc length of a sector with angle in radians, you do theta times the radius. If we just call the radius 1, I mean, it doesn't matter what you call your radius, because regardless of what you call your radius, what number you call it, you'll still get the same result. So we just call it 1 to make the problem easier. So theta times by 1 gives you theta. So this arc length is about theta. So theta is about equal to the height. The height is about theta. Now let's look at this right angle triangle. I'll call this O there, I'll call that A, and I'll call that B. So this right angle triangle OAB. So we've got sine theta, which is opposite over hypotenuse. We got a hypotenuse there of 1, an opposite of this height there. So therefore we can do height over 1. Height divided by 1 is obviously just height. So sine theta is equal to the height. And the height is approximately theta. Because we justify that over that. So that means that therefore we can say that basically sine theta is approximately theta when theta is a small angle. So when theta is small, it's approximately that. And a similar reasoning with the tan theta when theta is small. Tan is opposite over adjacent. Opposite to the theta is the height. The adjacent, now we're going to say that's approximately 1. So I mean, with this radius on the bottom there, again a radius of 1, but we're just going to say that this base there is approximately the same. This OB there is approximately the same. It's approximately the same as the radius, which equals 1 in this question. So all this like example. So we're going to say adjacent is approximately 1. So opposite over adjacent is approximately height over 1, and height is approximately theta. So approximately theta over 1. So that's equal to theta. So therefore, tan theta when theta is a small angle is approximately theta. So that's what we can say there. Now, how about cos? So cos is adjacent over hypotenuse. So you would get this OB adjacent side divided by the hypotenuse 1. You can assume that OB is approximately 1. So you would get cos theta is approximately 1 over 1, which is 1. I mean, yeah, that's true, but it's not really helpful getting cos theta is 1, because cos theta is only 1 when theta is 0. So that's not really helpful. So we really need to get an expression for cos theta in terms of theta. So yes, cos theta is, well, it is equal to the number 1 when theta equals 0. But obviously, when it's not equal to 0, it's not the number 1. So we just want to get an approximation in terms of theta rather than doing adjacent 1 divided by hypotenuse 1. So it's 1. We're going to try and get a proper approximation. So how can we do this? Well, I mean, there's a few ways we can do this, but this is one way we could do it. So cos theta is approximately 1 over theta squared over 2. So let's try and prove why this is true. So let's recall this identity, sine squared plus cos squared equals 1. So this is one of those key identities that you need to know. And if you don't know, if you've never seen this one before, the reason why sine squared plus cos squared is equal to 1 for any angle theta, so for all theta values in the real numbers. So this is true for every angle possible, and it's because sine is opposite over hypotenuse, cos is adjacent over hypotenuse. So sine squared is opposite squared over hypotenuse squared. Cos squared is adjacent squared over hypotenuse squared. So you've got a common denominator. So you've got opposite squared plus adjacent squared over hypotenuse squared. But using Pythagoras, your opposite side squared plus your adjacent side squared is going to be equal to your hypotenuse squared using Pythagoras. So you get hypotenuse over hypotenuse squared, and that's just the number 1 because they just cancel out to make the number 1. So that's where the formula comes from, but we'll go into these identities in more detail. So if theta is small, that means sine theta is theta. We just showed that on the previous slide. So sine squared theta is going to be approximately theta squared. So now let's plug that into the formula. So therefore we get theta squared plus cos squared theta is approximately, well, I mean, yeah, it's going to be approximately equal to the number 1. So cos squared theta approximately 1. So therefore that means that cos squared theta is approximately 1 minus theta squared. And if I just make my writing smaller, I get that cos theta is approximately the square root of 1 minus theta squared. Okay, so that's not what we wanted, but we're nearly there. So what we can do now is we can actually use binomial expansion. So this square root of 1 minus theta squared is the same as 1 minus theta squared to the power of a half. And now we can use our binomial expansion formula for fractional powers to do this, because now theta squared, is a small number. So we're assuming that theta squared has a modulus less than 1, which it does because theta is really tiny. So it's going to be definitely smaller than 1. So now we can use our binomial expansion formula. So remember, it was this formula here. So 1 plus nx plus n times n minus 1 over 2 factorial times x squared plus dot, dot, dot. So in this case, our x is going to be, so our x in this formula would be this theta, actually negative theta squared, sorry. So that's going to be negative theta squared. And then our n value is going to be our fractional power. So remember, it's that fractional power there, so a half. So we're going to swap, substitute x equals minus theta squared into the formula, and then substitute in n equals a half. Sorry, let me try and do that again, including the whole thing. So we will get, as a result, we get 1, and then so n is a half, so plus a half, times by x, which is minus theta squared, so minus theta squared, and then plus the rest of these. We actually don't need to worry about the rest of these, because you'll see right now we'll get the result. We get 1 minus a half theta squared, which is what we wanted to start with. So that's kind of how you can get this cos theta approximately equal to 1 minus a half theta squared, and also how you can get the other results back here using this geometrical argument: sine theta approximately theta and tan theta approximately theta. So that's just a general overview of your small angle identities, and you can use these to solve and approximate problems when you're dealing with small angles, and the question will be quite specific on when you need to use small angles.